Imagine you drop a pebble into a still pond. What happens? Ripples, right? These ripples are a disturbance in the water spreading outwards from the point where the pebble made contact. It's a simple yet profound phenomenon that we can observe in our everyday lives. These ripples spread out from where the pebble fell, disturbing the surface of the water. The energy from the pebble's impact is transferred to the water, creating waves that move outward in concentric circles. This is a perfect analogy for understanding a much grander cosmic event. Now imagine something similar happening in space itself. Instead of water, it's the very fabric of the universe that's being disturbed. This fabric is known as space-time, a concept that combines the three dimensions of space with the fourth dimension of time into a single continuum. Instead of water, it's the very fabric of the universe that's being disturbed. When massive objects like stars or black holes move, they create ripples in this space-time fabric. These ripples are not just theoretical, they are real measurable phenomena that travel across the universe. These disturbances, my friends, are what we call gravitational waves. They are waves of energy that propagate through space-time, much like the ripples on the pond. But unlike water waves, gravitational waves can travel through the vacuum of space, carrying with them invaluable information about their origins. Gravitational waves are one of the most mind-blowing predictions of Einstein's theory of general relativity. This theory, published in 1915, revolutionized our understanding of gravity, describing it not as a force but as a curvature of space-time caused by mass and energy. They are ripples in the fabric of space-time, created by some of the most violent events in the universe. Imagine two black holes colliding or neutron stars merging. These cataclysmic events release enormous amounts of energy, sending gravitational waves rippling across the cosmos. These ripples travel at the speed of light, carrying information about their sources and offering us a completely new way to study the cosmos. By detecting these waves, we can learn about events that would otherwise be invisible to us, such as the formation of black holes or the collision of neutron stars. In this essay, we'll embark on a journey to understand these enigmatic waves. We'll delve into the science behind their creation, the technology used to detect them, and the groundbreaking discoveries they've enabled. We'll explore what they are, how they were discovered, and the incredible story of the scientists who made it possible. The first direct detection of gravitational waves was made in 2015 by the LIGO Observatory, a milestone that opened up a new era in astrophysics, and why they are so important for our understanding of the universe. Gravitational waves provide us with a new lens through which to view the cosmos, offering insights into phenomena that are otherwise hidden from our view. Get ready to have your mind stretched, because we're about to dive deep into the fascinating world of gravitational waves. From the ripples in a pond to the ripples in space-time, this journey will expand your understanding of the universe and the forces that shape it. Okay, so we know gravitational waves are ripples in space-time, but what exactly does that mean, and why should we care about them? Let's dive deeper into this fascinating concept, but what does that actually mean? How do these ripples form, and what impact do they have on the universe and our understanding of it? It's a bit tricky to visualize because space-time isn't like the space we experience every day. It's not just an empty void, it's a dynamic, flexible entity that can be bent and twisted by the presence of mass and energy. It's more like a flexible fabric that can be stretched and squeezed. Imagine a trampoline. This analogy helps us understand how massive objects interact with space-time. If you place a bowling ball in the middle, it will create a dip. This dip represents how a massive object, like a planet or a star, warps the space-time around it. Now, roll a tennis ball across the trampoline. What happens? The tennis ball doesn't move in a straight line, instead it curves towards the dip. The tennis ball's path curves as it travels through the dip created by the bowling ball. This is similar to how planets orbit stars due to the curvature of space-time. That's kind of how gravity works, according to Einstein. His theory of general relativity describes gravity not as a force, but as a consequence of the curvature of space-time caused by mass. Massive objects like stars and planets warp the fabric of space-time around them. The more massive the object, the greater the warp. Now imagine two bowling balls orbiting each other on the trampoline. This is similar to binary star systems or black holes orbiting each other in space. They'll create ripples in the fabric as they move, right? These ripples are the gravitational waves propagating outwards from the source. Those ripples are like gravitational waves. They travel through space-time, carrying information about their origins and the nature of gravity itself. They carry energy away from the moving objects, just like ripples on a pond carry energy away from the pebble. This energy transfer can tell us a lot about the events that created the waves. These waves are incredibly weak, which is why they're so hard to detect. Even the most sensitive instruments can barely pick up these faint signals. But when something truly massive accelerates, like two black holes colliding, the resulting gravitational waves can be powerful enough for us to detect here on Earth. These events create waves strong enough to be measured by our advanced detectors. The detection of these waves opens up a new way of observing the universe, allowing us to study cosmic events that were previously invisible. It's like gaining a new sense, giving us deeper insights into the workings of the cosmos. The story of gravitational waves begins with Albert Einstein. In 1915, he published his groundbreaking theory of general relativity, which revolutionized our understanding of gravity. One of the astonishing predictions of this theory was the existence of gravitational waves. Einstein imagined these waves as ripples in the fabric of space-time, generated by accelerating massive objects. However, he also believed that these waves would be incredibly weak and nearly impossible to detect. For decades, scientists debated whether gravitational waves were real or just a mathematical quirk of Einstein's theory. The search for these elusive waves became a major challenge in physics. It wasn't until the 1970s that scientists made significant progress. Using sophisticated mathematical models and new technologies, they were finally able to design experiments sensitive enough to potentially detect gravitational waves. The quest for proof was on. The dawn of a new era. The first detection of gravitational waves. The year 2015 marked a turning point in the history of astronomy. On September 14th, after decades of searching, scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, made an announcement that sent shockwaves through the scientific community. They had detected gravitational waves for the very first time. The signal, a brief but unmistakable chirp, came from the collision of two massive black holes located over 1 billion light-years away. This cataclysmic event released an unimaginable amount of energy, briefly outshining the combined light of all the stars in the observable universe. This discovery was a monumental achievement, confirming Einstein's predictions a century later and ushering in a new era of gravitational wave astronomy. For the first time, we had a tool to listen to the universe's most violent events, unlocking secrets that had been hidden for billions of years. Cosmic Orchestra, unveiling the secrets of black holes and neutron stars. So, why are gravitational waves such a big deal? Well, they provide us with a completely new way to study the universe. Unlike light or other electromagnetic radiation, gravitational waves are not absorbed or scattered by matter. They travel through the universe unimpeded, carrying information about their sources directly to us. This is particularly exciting when it comes to studying objects like black holes and neutron stars. These incredibly dense objects are notoriously difficult to observe with traditional telescopes because they emit very little light. However, black holes and neutron stars are also some of the most powerful sources of gravitational waves. By studying these waves, we can learn about the properties of these enigmatic objects, such as their mass, spin, and how they interact with each other. It's like listening to the universe's own orchestra, with each gravitational wave signal revealing a new cosmic symphony. Echoes of the Big Bang, exploring the early universe with gravitational waves. Gravitational waves hold incredible potential for understanding the very early universe, a period just after the Big Bang that has remained shrouded in mystery. These waves are ripples in the fabric of space-time, created by some of the most violent and energetic processes in the cosmos. Because these waves can travel through the universe unimpeded, they offer a unique window into the universe's infancy, a time when light itself couldn't escape the dense, hot plasma that filled space. This period, known as the Cosmic Dark Ages, lasted for hundreds of millions of years until the first stars and galaxies began to form. Scientists believe that primordial gravitational waves, generated during the Big Bang itself, may still be rippling through the universe today. These waves would carry information about the universe's birth, providing clues about the conditions and processes that shaped its early development. Detecting these faint echoes would provide invaluable insights into the conditions present during the universe's earliest moments, helping us to test our current theories about the Big Bang and the evolution of the cosmos. By studying these waves, we can learn about the fundamental forces and particles that govern the universe's behavior in its first fractions of a second. While we haven't directly detected these primordial waves yet, scientists are actively searching for them using a variety of techniques. Advanced observatories like LIGO and Virgo are constantly improving their sensitivity, hoping to catch these elusive signals. Additionally, future missions like the space-based LISA Observatory aim to detect gravitational waves with even greater precision. The quest to find these echoes of the Big Bang is one of the most exciting frontiers in modern cosmology, promising to reveal secrets about the origin and evolution of our universe. As we continue to push the boundaries of our knowledge and technology, we move closer to uncovering the mysteries of the cosmos and understanding our place within it. The discovery of primordial gravitational waves would not only confirm key aspects of our cosmological models, but also open new avenues of research, potentially leading to groundbreaking discoveries about the nature of space, time, and matter itself. If you like this video, don't forget to like and subscribe. See you again on the next video.